طيب شباب السلام عليكم.
وعليكم السلام.
وعليكم السلام.
طيب, welcome back after this super long weekend. So today, inshallah, we'll continue our discussion on k-anonymity. Before that, please remind me, I posted homework 1 on Blackboard. So it makes more sense to go over it after finishing the discussion, because most of the, but at least, like the 3 to 4 questions in the homework is related to the material that we're going to discuss today. Okay, so please remind me in the last maybe 5 to 10 minutes of the lecture. I can, if I did not finish, I'll stop and go over the homework assignment so that it will be more clear to you. Okay. And before we start discussion, do you have any questions regarding the previous material, regarding the quiz? So I believe I went over the questions on the quiz last time, and I already graded all the graded your answers, I think yesterday. So please, if you have any questions regarding the grading of any question, especially that controversial essay question, I would say, please let me know. Okay. So for some of you, I left some comments. I didn't really get what do you mean in your response. So if you feel that you want to clarify and maybe you deserve like a full mark, just let me know. Okay. So maybe you can send me on Teams or send me an email. Again, any questions? I'll leave.
Can we know what's the average of the average score?
It's about 9 out of 12, so about 75%.
Okay.
Right. Okay, if you don't have any questions, so let's move on. And I think now we are almost in week 5, so we have to take things a little bit quickly, or like a little bit fast. So I think we have, I forgot to mention, maybe we'll have a quiz next week regarding the k-anonymity. I will post the announcement by end of today or so. So last time we discussed about the k-anonymization, which is a technique that is used to preserve the privacy of data set that is being shared or published, right? We said that like data sharing and data publishing are kind of two terminologies that we use if we want to release some data set that we have, but releasing data set might result in some privacy violation, right? And we have a case of that data linkage attack, both from the Massachusetts governor case and the Netflix prize case. And they said we as a countermeasure or as a solution, researchers propose what is called k-anonymized, okay, or k-anonymity, or k-anonymization. In fact, it's called k-anonymization. But when we say that a table is k-anonymized, is if a record, right, cannot be identified from another or from other k-1 records. So in other words, what we are doing with the table is to group records together in what is called equivalence classes, and each equivalence class has a size of k or more records. Okay, so in this case we have a table and we have 2 equivalence classes, and in each equivalence class we group the records based on their quasi identifiers, which are job, sex, and age. Group 3 records together, right? And in the second equivalence class we grouped 4 groups together, or 4 records together, right? So what is the minimum size of the equivalence classes? It's 3, right? So in other words, what we mean, this table satisfies what is called 3 anonymity, right? Where k is equal to 3. So k is just a variable, it takes any value, right? So in this case it's 3 anonymization. If in case of 4 anonymization, the size of each equivalence class has to be greater or equal to 4, greater than or equal to 4, and so on, right? So in general, if we have a K anonymization, right, then we have all the equivalence classes must be of size K or more. Make sense? So in this case, in this particular case, we have K is equal to 3. So let me ask you this question just to warm up, right? If we have this table, which is row table, right? What is K in this case? What is the value of K in this case?
1. 7.
K is equal to 1, right? Because if think about it, if we have one anonymized, it means that we have each equivalence class is of size 1 or more, right? But in this case, has to be of size 1 or more. In this case, each record by itself is an equivalence class. So the first record is an equivalence class, the second record is an equivalence class, and so on. So what is the privacy here? So in other words, what is the probability that if we know some quasi-identifier for the first record, we're going to identify him by the quasi-identifier? It's absolutely 1, right? Because 1 over 1, K is equal to 1, and the identification was 1 over 1. So there is no privacy, right? So K anonymization, right, or K anonymity in this case, start to make sense for values of K greater than 2, greater than or equal to 2, right? And of course, the minimum or the least privacy is when K is equal to 2 exactly. And we'll have an example in a minute. I hope that K anonymization is clear to you. If it is still not clear, we will go through an example where hopefully the concept will be cemented. How can we achieve K anonymity? We said by many ways. One of them is called a generalization, right? So generalization basically is by replacing the value in the quasi-identifier attribute with a more generalized value or a more less specific value. What does that mean? Suppose that we have a job attribute, and in the job attribute we have several values like engineer, lawyer, and admin. What we can do is we can replace those values with a more general value, for example, professional. Okay, so in other words, we're replacing a specific job title with a more generic job title or a less specific job title. So, by the way, in this case, job is called categorical attribute because it takes categories, right? Engineer, lawyer, admin. Sometimes we have numerical values like age. We have 35 to 36 to 39. And in this case, generalization is straightforward by using range. So age, rather than these values, we can replace it with a single value that represents the range from 35 enclosed or closed to 40 open, right? So in this case, as you see here, we replace the age of all those records with this range. In the same thing, job, like engineers and lawyers, we replace them by professional, right? So sometimes it's really difficult. By the way, the generalization, in order to make this generalization, you need to construct this tree or generalization tree for every attribute. And this have to be, carefully built. Like it has to be aware of the syntax, the semantic of the attribute. If you have jobs, age, for example, sometimes zip code, and salary sometimes, right? So you need some domain expertise in order to build this generalization tree. And sometimes it's really difficult to generalize a value. For example, if you have a male or female, right, there are only 2 options. So how can we generalize that? In this case, we resort into another approach, which is called suppression, which is basically replacing or removing that value, that attribute, and replace it with an asterisk. So asterisk, think about it as a wild card, right? So it means that anything, right? So in this case, it's either male or female. Okay. So I think K refers. Khatim has a question. So K refers to the number of quasi-identifiers that are anonymized. No, that is not what I meant. K, in this case, is the minimum size of each equivalence class. This has nothing to do with the quasi-identifier. Okay. The quasi-identifiers are the one that will be generalized. The values in the quasi-identifier attributes, that are the one that will be generalized in order to construct these equivalence classes. Make sense? So K is not really the number of quasi-identifiers. It's really the size of each equivalence class. So in this case, we have 3 anonymized, right? So each equivalence class in this case, which are 2, is of size 3 or more. That is what is meant by K. I see Hussein has a question. تفضل.
Yes, Doctor. If we are replacing the data with asterisk, why do we include it at all? If we are just putting asterisk, it means it's not shown. So why do you include it to the table?
Right. A good question. Sometimes, like in the equivalence class itself, we cannot generalize it, so we put asterisks, right? But in that attribute or in that column, other equivalence classes might show some values. So we have male, for example. But you are right, if all the equivalence classes, right, in that attribute, we're not showing anything, we can remove that column altogether. Okay? But sometimes we will, in order to improve or convey as much data as we want in this data set, sometimes in some equivalence classes we remove data, and in other equivalence classes we have some data, right? So in this case, in sex attribute, in the first equivalence class we have male, right? So some data, and in the second equivalence class, we are removing the values, so we just put in asterisk. But we cannot remove the column, sex column, because really it conveys some information after all, right? So your question is valid. If all the columns if all the values in that columns are in asterisk, we might remove that column. Doesn't matter, right? Hussein, go ahead.
Hello. In some researches, we need the age or the sex, the specified age, like
right.
For medical research.
Right.
So how can we achieve anonymity?
Good question. So as you said, sometimes it's really important to preserve this value of male and female, right? Being being gender. So there are some algorithms, okay, that can take this particular information. Let's say, for example, in order to provide a K anonymity table, please preserve the value of our sex. Don't generalize it, right? So the algorithm will take care of that, right? But the algorithm that we're going to learn today is, let's say, agnostic about all these restrictions. So as I told you, there are many variations of the co-anonymization algorithms that kind of, give you, that take care of these corner cases that you just mentioned. But again, it all depends on the context and the final objective. What are you trying to, achieve with this data that you are anonymizing? Make sense? So
yes.
I'll come back to your question once I go over the algorithm. So as I mentioned maybe last time, there are other methods. Let me go over this and I'll come back to you, Mahmoud. For example, perturbation, right, which is different than generalization and suppression. And the idea here is to add noise, errors. So rather than, for example, give the same age, I'll add ±2 years. Rather than having or revealing the same salary, I add, let's say, ±500 riyals, and so on. So just adding noise. And this noise has to be controlled, has to be, carefully added, so that when you do analysis later on, right, you can remove this noise and get back to the original result. And this is actually what is the objective of what is called statistical data privacy, which is, inshallah, next topic. But we're not going to learn it for now. And there is also what is called data generation, basically fake some records in order to construct this equivalence classes, right? In order to satisfy the K anonymity requirements. Mahmoud, do you have a question?
Yes, Doctor. Under what condition or what is the attributes that we can build equivalence classes? What is the attribute?
Good question. See, in the definition, it always depends on the quasi-identifier, right? Remember, in the table, we had 3 types of attributes. the key attributes that identify a person by itself, by himself, and that's also removed. We don't want to publish that. And then we have the sensitive attributes, right? So these sensitive attributes, the value has to be shown as is. You don't change it. So we have only the quasi-identifier. Those attributes that are defined as quasi-identifiers need to be changed, need to be generalized or suppressed. So in this case, in this table, we have job, sex, and age are the quasi-identifier, while disease is the sensitive attribute, right? So the values of those three columns, job, sex, and age, are the only one that will be generalized or suppressed. Make sense? So you look at the definition. A table is k-anonymized if each record cannot be identified from other k-1 records with respect to quasi-identifiers only. Make sense?
Yes, yes.
So now let's go to an algorithm. So just to show you some how hard is this problem. There is a set of problems in computer science. It's called NP-hard problem. These problems are really hard to solve, but there is no proven algorithms to solve in polynomial time. It turns out this k-anonymization algorithm is one of them, right? So it's not an easy job to get this data set and find a k-anonymization or k-anonymized version of this table. So, but there are some heuristics, so there are some fast algorithms that give us a pretty good enough k-anonymized versions, and one of those algorithms is called greedy partitioning algorithm. And the idea is very simple, okay? And I'll explain it in a minute, and then I'll go over the steps. Suppose that we can represent the table in using a two-dimensional space, where in one dimension we have the age, and the other dimension we have zip code. So those are the only two quasi-identifiers in our table. We can represent each record with a point in the two-dimensional space, right? So in the first record, the age is 25. He lives in 53711. The second one lives in 53712. He has age 25, and so on. So in total, we have 6, right? Now suppose that we want to create a k-anonymized version that is of the table that is equivalent to cutting or grouping those points into what is called partitions. In order to satisfy the k-anonymity, remember, what was the k-anonymity? Each equivalence class has to be greater than or equal to the size of the anonymity equivalence class has to be greater than or equal to k.
1 over k. 1 over k.
No, 1 over k is the probability of linking.
Oh, okay.
The size has to be greater than or equal to k.
K, yes.
Similarly here, the partition has to have k or more points, right? So the size of each partition has to be greater than or equal to k. In this case, we have k is equal to 2. So the partition has to be, each partition or each equivalence class has to have k or more tuples. So in this case, we were able to cut or partition the space into 3 equivalence classes, where each one has exactly 2 points, right? So if we were able to, reduce the table into a 2-dimensional space and start cutting, then we will achieve the same result. The problem is, what happens if we have three quasi-identifiers? Let's say age, zip code, and let's say, for example, salary. So we have a 3-dimensional space. How about if we have 4? It's going to be 4 dimensions. So it's going to be difficult for us to do the same thing, right? So that's why it's really difficult to create it on a multidimensional level or 3 or more quasi-identifiers. But fortunately, there is an algorithm that is based on KD tree. You don't have to go into the details. Basically, this is the steps. This is the pseudocode, okay? And I will go over I will go over it with an example rather than go over the steps one by one. I will go over by an example. This algorithm takes two inputs: the table itself and the value for k, right? Because k determines how are we going to group the records together in order to find or to construct equivalence classes. In this case, we chose k to be equal to 2, and then we will show you. I will discuss the limitation of this algorithm in a minute. And we identify the quasi-identifiers to be zip code and age. So only 2 quasi-identifiers. Forget about the sex, okay? Only the age and zip code. Those are the 2 quasi-identifiers. And again, the idea is that we want to construct a 2 anonymized version or table of this raw data. So this is the final product, right? So you see at the first 2 columns, they have exactly the same values in terms of age and zip, right? So to have the 25, 26 and the same zip. And the second or the second 2 rows have exactly the same values in terms of age and zip, and so in the last 2 columns. And notice how that I shuffled some of the records, right? In a minute it will be clear. So let's go over the algorithm. How are we going to do it? So this is the first iteration. We take the full table. The first step is to to partition it. In order to partition this table, we need to decide on a dimension, or what are we going to cut, or what are we going to partition this table based on. Like in other words, I need to choose a quasi identifier, right? To group the records. In this case, I will choose the zip code dimension. Okay. Actually, there is a method or a way to find the dimension. I will explain it in a minute. Once we identify the zip code as a dimension, I will create what is called a frequency set. What is a frequency set? We take each unique value in that attribute and find its frequency. So, for example, 53710. How many times it occurred? Only once. So the count is 1. 53711, which is another unique value, occurs 3 times. Okay, so the frequency is 3, and so on for 53712. Make sense? Now, the second step is to find a split value, a value to split this table based on, and we decided that the split is 53711. Okay, and actually the algorithm says you need to find the median value. So the median is different than the mean, right? The median is you have to order the values in ascending or descending order, it depends, and then find the value, right, that has the kind of comes in the middle, right? That can kind of have the like the if you order the values, right, the median is the one that is exactly in the middle. So in this case, 5371 is the median value, right? So now we're going to split this zip code or the table based on values of zip code. So we'll come up with two tables: a right-hand side with zip code greater than 53711, and a left-hand side table with zip code that is less than 5371. Oh, sorry, less than or equal to 53711. Right? So we have a right-hand side of those 2 tables and a left-hand side of those 4 records. Make sense? And now then we're going to do it iteratively. So we're going to take the left-hand side table and start partitioning it one more time. So we'll take this, and in this time, we're not going to take the zip code. We're going to take the age as a way to partition the table. And then again, we build the frequency set, and it happens that the frequency set, or each unique value in terms of age, occurred 1 time. Okay. So in this case, the median value we decided to be 26 or 27. It doesn't matter. It depends on like your criteria of cutting or of choosing the median. So once we find the split value to be 26, again we're going to cut the table, this partition, into 2 tables: a right-hand side with values of age greater than 26, and a left-hand side with less than or equal to 26. So we result into 1, 2 tables, plus from the previous step we have 3. So we have in total 3 subtables, each of size 2, right? So this right-hand side is of size 2, and the left-hand side we further in the next step we group it or partition it into 2 left-hand side and right-hand side, and it happens that all the partition is of size 2. Remember, our value was of k was what? Was 2, right? Now the question is, can we do anything better? Can we split these these tables, these subtables, into smaller tables?
It's the smallest thing.
It's the smallest thing, right? Because k equal 2. Now that's it. We stop. So in other words, the algorithm has to mechanically go over it, right? So we will take the left-hand side table from the iteration number 2, and we check. Is there any allowable cut? No, there is no allowable cut, right? So now we generalize. So what are the values for age? It's 25 and 26. So we replace it with the range 25, 26. Is there any way to generalize zip code? No, because it's just one value. So we replace it with, or keep it as is. We take the second, the right-hand side from the second iteration and do the same thing, no allowable cut. And we replace the age with 27, 28. The zip now, because look at the zip code, we have two values, right? So we can generalize it as 53710 to 53711. And then we left with one more table from iteration 1, right? There is no more allowable cuts.